Hi everyone, my name is Niloofar Yazdani. I'm working under the supervision of Professor Daniel Lokani. I'm going to be talking about multi-source data compression and age of information analysis. By 2027, the number of IoT devices is expected to be 41 billion compared to 8 billion in 2019. This growing number of IoT devices face communication bandwidth constraint and have a limited lifespan, which is mainly due to the energy consumption by wireless transmission of data. To reduce the amount of data transmission, a wide range of lossy and lossless compression techniques have been proposed so far. However, lossy compression techniques have a potential to provide a good compression, but they are not suitable for all applications, for example, for compressing financial information. And that's why we need lossless compression techniques. But there are two main problems. First of all, lossless compression techniques compress data on individual devices, and furthermore, they have a limited performance on short data. In 2019, our group proposed generalized duplication, which is a lossless compression technique. And generalized duplication first expands the data into equal size data chunks, and after that it applies a transformation function to each chunk to map each chunk to a basis and a deviation. The basis is the large part of the data and carries most of the information. For the transformation functions, different transformation functions have been used so far. For example, the decoding function of an error correcting code. But to see how generalized application works, let us take an example. The figure shows some chunks. If we assume that chunks have a shape and a color, then if we apply data deduplication, in this example, we cannot compress the data because our chunks have either different shapes or have different colors. But if we use generalized duplication, then generalized duplication can define a transformation function that maps the chunk into the shapes, which would be our bases, and the colors, which would be our deviations. And then if we apply deduplication on the basis, then we can compress the data because we don't need, for example, to save the squares twice, but we can only save them once in the basis. And our goal here is to use the concept of generalized duplication to design a communication protocol which is suitable for short data generated by IoT devices. To explain our data transmission protocol, I'm going to use an example. Let us consider that we have several source nodes and we have a sink node. Then our first source node has a chunk of the data, and it applies generalized duplication to map the chunk into a basis and deviation. If the sink node receives the basis and deviation, it can reconstruct the chunk itself, but the source node sends the basis ID and the deviation instead of sending the basis and deviation. And for generating the basis ID, for example, we can use a hash function, which is common between all the source nodes. Then when our sink node receives the basis ID and deviation, it checks whether it has the basis for the basis ID or not. And since it doesn't have it, it sends a request for the basis itself. And by receiving the basis, it sends back an acknowledgement. So far, we haven't compressed the data yet, but after receiving that, now we imagine that our source node has a new piece of data which is mapped to the same basis but a different deviation. Our source node sends the basis ID and the deviation, and the sink node checks whether it has the basis for the basis ID or not. And this time, the sink node has the basis because it has previously received it in the previous transmission. So it sends back an acknowledgement, and this time we compress the data because the source node didn't have to send the bases, which was the large part of the data, and the bases ID is shorter than the bases itself. But let us take another example. We have also another source node at our network, and this source node has a different piece of data, which is mapped to the same bases, but of course a different deviation. Then this source node sends the bases ID and the deviation to the sync node, and the sync node checks whether it has the bases ID for this. It checks whether it has the basis for this basis ID or not, and since it has it, it sends back an acknowledgement. So the interesting thing here is that it doesn't matter if this basis belongs to this source node or not. As long as our source node uses the same hash function for generating the basis IDs, we will be fine. So we can use the previous data from all the source nodes to compress the data. I would like to analyze this data transmission protocol in terms of age of information and in terms of compression gain. Compression gain is simply we measure the size of the compressed data and we measure the size of the original data and we calculate the compression where a higher value is better. But for the age of information, first I'm going to give a short overview of what is age of information. In many applications, such as live video streaming, we need the data to be delivered at the sync node in a timely manner. And age of information is a metric that quantifies the freshness of information at the sync node. One way to reduce the age of information could be using online compression strategies to reduce the amount of data that needs to be transmitted. But there's another factor which is affecting the age of information, and it's that many advanced compression techniques require collecting enough data to provide a good compression, and the time needed for collecting this amount of data can affect the age of information negatively. But let us take a look to see how it works for our protocol. So here we are comparing our technique, which is called GD here, which comes from generalized application, with 3 other well-known compression techniques: data deduplication, LZW, and deflate. And we are comparing in terms of compression gain and normalized average age of information. We are considering 4 real-world data sets. And for the figure at the top, a higher value for compilation gain means a better result, and the compression gain of 1 means that we don't have any compression. And we can see that our technique shown with blue color provides the best compression gain for 3 data sets, for Hyundai and Toyota. And if we take a look at the figure at the bottom, we can see that our technique provides the best average age of information, because for age of information, a lower value is better. So we are better than other techniques for the 4th Hyundai and Toyota data set. And if we consider the temperature data set, we are almost as good as data duplication and LZW, and better than deflate. And here we are considering another factor. For deflate and LZW, we need enough data to provide a good compression. And that's why here we are bundling chunks together so that we increase the size of data and we increase the compression gain for these 2 methods and see what happens. The numbers which are close to these markers here show the number of chunks that we bundle together for deflate and LZW. And number 1 means that we are using the same chunk size here as the one that we are using for GD and for DD. And number 2 means that we are bundling 2 chunks and so on. And we can see that by bundling more and more chunks, we are improving the compression gain for compression for deflate and LCW, but at the same time, the average age of information is getting worse. So there is a trade-off between compression gain and age of information for these two techniques, but generalized application removes this trade-off. We can have a good compression gain and good average age of information in generalized application, and we can see that here there is a black square which shows the ideal case here where we have the highest compression gain, because this y-axis shows 1 over compression gain, and it shows the lowest possible average age of information, and the closer that we are to this ideal case, the better results that we have. And we can see that the best result is achieved by our technique, which is shown with the star here. My PhD focused on 3 main projects. What I just presented was one of them. Apart from that, we also proposed revolving codes, which is a new network coding approach that reduces the overhead and complexity. Furthermore, I am currently a visiting student at TU Delft, and with collaboration in teams from TU Delft, we proposed redcasts, which are algorithms to recover data from corrupted frames. During the PhD, I had authored a total of 11 publications, which 2 of them are to IEEE IoT Journal and IEEE Communication Letters. And in 2019, for our idea on revolving codes, we were awarded a Best Paper Award from the Vehicular Technology Society. And furthermore, I had the opportunity to collaborate with teams in Chemistry and CSS Electronics to compress the data. And also, I collaborated with teams in the University of Neuchâtel to propose Hermes protocol. And I collaborated with Associate Professor Aranha from Aarhus University as a member of the Security Work Package. Thanks for your attention, and I'm open to questions.